Hello, everyone, and say hello once again to Virtual Greg. Before we begin today, I do just want to point out that in case any of you have some spare time to celebrate, today is E-Day. Now, I know it's not as famous as a certain other irrational number, namely pi, which you can celebrate on March 14, but E, or Euler's number, happens to be part of the definition of, among many other things, the shape of the normal distribution, a distribution that we will encounter quite a bit over the course of this class. So you can see here is the equation, and here is E, Euler's number, featured prominently. Now, I do want to point out that Euler didn't pick the name E for his own name. That came around later, but yeah, still, if you have some time, if the university finally realizes that people shouldn't really be on the roads, then maybe you have some time to celebrate E-Day. So, yeah, getting back to it, today we're going to be finishing up our tour of measures of central tendency. So last time we talked about the mode and the median and discussed a number of properties of each of those measures and when you might prefer one over the other. Today we're going to devote a fair amount of time to discussing the mean, or the average, which is a term that probably everyone very closely associates with statistics, and so I thought it deserved a bit of special mention. And then at the end, once again, we'll kind of get together and compare the mode, the median, and the mean as different measures of central tendency. What sorts of things do they tell you, and when are good situations to use each. And to begin, yeah, I just want to bring us all back to the big notion of what we want out of a measure of central tendency. So once again, we're looking for a value that is representative of the kinds of values that we have observed. And this value should help us to summarize the data. If we tell someone this value, it should give them at least some idea of what the data look like without them actually having to look at the raw data itself. So, as a kind of analogical problem, we can think of how might you summarize this weather. So, I will say that I made these slides long before today's current weather, so we can think of this maybe as aspirational, but so how would you summarize this weather? So there's a lot of clear patches, some clouds as well. So if you are the mode, you would just say, clear skies, because the mode only picks up on the most common feature of the data, the most commonly occurring value. So in this case, this is the most commonly, it's kind of going over there, but you understand, the bottom there is the most commonly occurring color in this picture. So, yep, clear skies seems pretty good. If you're the median, you could say, well, it's mostly clear. So the median value, it's still fairly blue, maybe a little more faded out, but at least tells you that, okay, yeah, the most of the sky, in other words, the stuff that's less blue than this, is pretty clear. And if you're the mean, what we'll be talking about today, it actually tells you something a little bit more. It says, well, it's mostly clear, but it's partly cloudy. And you can see that this is beginning to get kind of more gray. It's telling you not only what the most common values are, but it's also influenced by some of the more uncommon values, like these clouds that pop up here and there. So, like I said, this is something of an analogy, but hopefully gives an idea of the different flavor of each of these measures of central tendency. So, to remind everyone of our ongoing example for the time being. We're looking at data from the 2015 running of the 50-mile course at the Virgil Crest Ultra Marathon Series. And what we were looking at last time was the question of how quickly do people finish the race. So to remind everyone, what we have are these data, which are time to finish for each finisher as measured in hours. And last time we found that the modal interval, in other words, the range of times that were most common for people finishing, was between 14 and 15 hours. It's right here. And the median finishing time is a little over 13 hours, which, as we noted last time, kind of seems to mark a divide between this big hump of relatively slower times out here and this kind of smeared out section of faster times below it. Now, we also, though, noticed that neither of these measures were particularly sensitive to what would seem to be fairly drastic changes in the underlying data. So if we move the longest finishing time around, these two measures are unaffected. Now, the mean, though, is going to be sensitive to such changes. That's what I meant in the previous example, where the mean tells you not only that it's mostly sunny, but also that it's partly cloudy. It's influenced by all the parts of the data, and we'll see what I mean by that as we go through the lecture today. So, well, just to make it more concrete, the mean itself, which you've probably encountered in some sense, is relatively easy to compute as long as you've got a calculator. So assume that we had these data. These are just the fastest finishing times, but we've got 5 of these. And if we wanted to find out the mean of this set of observations, what we want is the sum of the observations divided by the total number. So that expanded looks like this. So in the numerator, we have the sum of all the observations, and we divide that by the total number of observations. So if we, again, take out our calculator and plug in these numbers and keep going, you can see my slide animation didn't quite work, but so it kind of gave away the ending. But the average finishing time, the mean finishing time for this set of data is 8.8 and some change hours. So if we do this for our complete set of data, again, all we're doing is adding each of these things up and dividing by the total number of observations, which in this case is 60. So the sum of all of these guys, you can check it for yourself, is a little over 768. And we divide that by 60 to get about 12.8 hours being the average finishing time. So that's where it would show up on our graph. And you'll notice that, and we'll see more of this as we go, the mean seems to be kind of pulled out towards these faster times here, and away from either the median or the mode, which tend to stick closer to the most common values of the data. So to illustrate how the mean is strongly influenced, or at least can be strongly influenced by each value in the data, let's do what we did last time and pretend that the slowest finishing time was actually really, really super slow. So let's say it was over a day, 24.6 hours. So in that case, if we do the same thing, just take out our calculator, add up each of these numbers, divide that sum by the total number of observations, which is 60, we get 12.9 and some change hours. So we've gone, our average time by changing just a single observation has gone up 1/10 of an hour, which in the grand scheme of things, maybe not so much, but it does illustrate how unlike the median and the mode, the mean is very sensitive to changes in the underlying data. So just to give some more formal definitions here, the mean, sometimes called the arithmetic average. There are different kinds of averages that we won't be using, but yeah, usually average is sufficient to describe this term. So mean or average of a set of observations is the sum of the observed values divided by the total number of observations. And because it's the sum of every observed value is used to compute the mean. So this is what I meant last time when I described the mean as sort of being able to see all of the data and be affected by every single observation that you've got. And just to, on a notational level, sometimes we refer to this, the mean, as the capital letter M. That's sometimes used, or I tend to use this more by habit. Yeah, just a matter of course, but it can also be referred to as the Greek letter mu, and yeah, so pronounce mu like a cat would say. Now, an interesting thing comes up that illustrates some of the kind of unique properties of the mean when we think about how we might try and compute it instead of just taking the raw data, but doing it from a frequency table. So in this case, I'm going to go back to an earlier example and excuse me, say that we have a set of quiz scores, which are whole numbers out of 10. And so, as usual in our frequency table, what I've got is an X column that indicates each value that we have observed. So 5, 6, 7, 8, 9, 10. And for brevity, I didn't include lower values since, we didn't observe any of those, but in principle you could. And because in this column here, the F column, we have the frequency with which each score was observed. So 3 students got scores of 10, 8 students got scores of 9, 9 students got scores of 8, and so forth. So the first step, if we want to compute the mean from this frequency table, is to come up with a new column, which, if you'll excuse the poor formatting here, is the score times the number of times we saw it. So this would be 10 times 3. So we saw the score of 10 3 times. 10 3 times, that gives us 30. 9 times 8, 72, and so forth. So again, this is just some fairly simple arithmetic, but we summarize it using this variable notation. So x times f looks like that. And what this actually is doing is saying, it's basically transforming the frequency table back into the raw data. So what we do, we say 10 times 3, well, that's 10, 10, 10. And then 9 times 8, that's 8 nines. So 1, 2, 3, 4, 5, 6, 7, 8, and so forth for all of the numbers. So what we're doing is basically a mathematical shorthand for writing out the complete set of data based on this frequency table. And at that point, the mean is once again just kind of mechanical. So as we recall from when we were talking about frequency distributions last week, the sum of the frequency column must be the total number of observations, n. So if the mean is the sum of the observations divided by the total number. That's given in this case by the sum of this column times the frequency with which each was observed. So we can do this either by doing it in this column way, so we do 10 times 3 is 30, and then add 30 and 72 plus 72 plus 28 plus 30 plus 10, or we can do it the kind of more more mechanical way that's perhaps more appropriate to the definition of the mean. Just rewrite the data as this way and add them up like this. So 10 plus 10 plus 10 plus 9 plus 9 plus 9, etc. And either way, that gives us a total total quiz scores being 242. And then we had 31 quiz scores, so the sum of the frequency column, which is the total number of observations, is 31. Divide 242 by 31, and we get about 7.8. Now, we can think of this as saying that the mean is the sum of the observed values, but they are weighted by how often they occur. So think about that. The mean, sure, it is the sum of the observed values divided by the total number of observations, but particularly in the case of situations where we have repeats of the same observation, it's as if a repetition is lending that observation a little bit more weight. So it pulls the mean in that direction. And we'll see that again in, I believe, the very next slide. Another thing to note here is that the mean, which is 7.8, is not a value that we could have ever actually observed, because quiz scores are always going to be a whole number out of 10. So it's impossible to actually score 7.8 on this quiz. So, unlike the mode or the median, the mean may be a value that is actually impossible to observe. But now to go back to this notion of the mean being some kind of a weighted sum of the observations, we can think of the mean as solving a particular kind of problem, namely trying to find the point at which a data set is balanced, you might think. So imagine that we have our possible scores laid out on a flat surface like this, and let's say we observed just a single quiz score of 7. Well, if we wanted to put a fulcrum underneath this surface in such a way that it would be perfectly balanced, in other words, it wouldn't fall down either to the right or to the left, what we need to do is put that fulcrum right under the observed value. So it's perfectly balanced. So in this case, the mean of this data set, which just consists of a single number, 7, is 7. Easy enough, right? So once again, the mean, the total, is the sum of all the observations divided by the total number of observations. So 7 divided by 1 single observation gives us a mean of 7. And this is the balance point for this data set. It's the point at which this surface would not fall either to the right or to the left. If we got another observation, let's say we saw a quiz score of 9, well, we couldn't leave our balance point at 7 because then it would the surface would fall. 9 would pull this down. So what we have to do is move the mean up to 8. So it's, again, in this case, the midpoint between 7 and 9. So again, you can do the computations yourself, but we have 7 plus 9 divided by 2, so it's 16 divided by 2, and that gives us 8 as our final mean. Now what happens if we observe a score of 6? Well, in order to keep things balanced, we're going to have to move that fulcrum, move that balance point once again. We have to move it away from 8 because then that would cause if we left it there, that would cause this surface to fall down on the left side. And so we have to kind of nudge it a little bit over. And we don't want to nudge it too far towards 6 because if we did that, then this extra weight at 9 would cause the fulcrum to fall down. So we have to nudge it just a little bit. And it gives us about, so this is 7 1/3. So about 7.3 is the balance point for this set of data. And our mean, once again, definition just comes from this. So 6 plus 7 plus 9 divided by 3, that's about 7, well, it is 7 1/3. So it's about 7.3. Finally, we can kind of nudge that mean back towards 7 one more time if we have a second observation of a score of 6. So you'll notice here that the mean is equal in the very first case and the very last case, but the set of observations that we use to compute it is rather different. But in either case, it is the point at which all of the forces exerted by the observed data are equally balanced. We've got extra weight at 6 that's pulling down pulling down the surface on the left, but that's balanced out by this far out single observation, the single weight at 9. So once again, the mean is the point where the scale is balanced, where the surface doesn't tip either to the left or to the right. And this is what I mean when I said that you could think of the mean as being a sum of the observed values weighted by how often they occurred. Because you can think of each observation as adding weight to a particular value. So we saw 2 6s, and that puts extra weight on this point of the scale. And so we need to move the balance point in order to accommodate that extra weight. So just to reiterate, we can think of the mean as being the sum of the observed values weighted by how often they occurred. And if I could go back to, if you'll excuse my clicking here, to go back to this representation in terms of a frequency table, well, so the frequency table is a useful summary because it means that we don't have to write out every single observation like this. Instead of writing out 10, 10, 10, 9, 9, 9, 9, etc., we can just write, there were 3 10s. And there were 8 9s. And there were 9 8s, and so forth. But if we didn't care about saving space and kind of being efficient this way, what we could do is write out a frequency table where we had a row for each of these observations. So it would be 10, 10, 10, 9, 9, 9, etc. But where the frequency column was just 1 for each of these. So it would be 10 times 1 plus 10 times 1 plus 10 times 1 plus 9 times 1 plus 9 times 1, etc. Now, this would be kind of an inefficient way of doing it, but what I hope this illustrates is when we have situations where there aren't necessarily repeated observations. So, for instance, like the finishing time data we have, it's exceptionally rare, although not impossible, for two runners to finish at exactly the same time, so you would rarely have a frequency that was greater than 1. Nonetheless, each of those observations is being given, is essentially being given equal weight when you're thinking about things in that way. When you're thinking about writing out sort of a what you might call a degenerate a frequency table, so a table where the frequency column was always equal to 1. But nonetheless, it still works because what you're doing is finding the balance point between the observations, and each observation is just adding weight to a different point on the scale. And this comes, or this thinking of means as being related to weights and finding a balance turns out to be particularly useful when we have to compute something that's called a weighted mean. And a weighted mean is a mean that combines the means of different samples, but where the samples that were used to compute each of those means may have different size. So intuitively, you would think that if samples are not of equal size, then they shouldn't exert equal influence when we try to make a combined mean, a weighted mean in this case. So what we want is to find a way to balance those two things. Well, the weighted mean is just the sum of the observed means weighted by the size of their corresponding sample. So let's imagine that we had two samples of quiz scores, one with a mean of 7 that came from 9 students, and one with a mean of 9 but that only came from 3 students. So if we wanted to find the weighted mean of these two samples, what we have to do is think about them like this. We think about there being, okay, we're going to pile a lot of weight on 7. In particular, we're going to do it 9 times. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And we're only going to give a weight of 3 to this observation 9. So 1, 2, 3. What does that look like algebraically? Well, that's just the same thing that we did when we were computing the sample mean from the frequency table. What we had there was a number of observations in a single sample, but here it's across 2 samples. So what we have is 7 times 9 plus 9 times 3 divided by the sum of the total number of observations, which in this case is 9 plus 3, which is 12. And that gives us, in the end, a value of 7.5. Once again, let me do it verbally, just so you can kind of write out the equations on your own, see how those go. The weighted mean is computed just the same way that we were computing means from frequency tables. So it's we can imagine this as being like the x column, and this as being like the frequency column. 7 times 9, it's what? 7 times 1 is 3, plus 9 times 3, 27. Divide that by 12, and we get 7.5. Now, an important thing to point out in this case is that the weighted mean, because we are taking into account the fact that they came from samples of different sizes, is not just halfway between 7 and 9. So a naive but wrong way to do this would be to just say, let's just take the midpoint between 7 and 9. So that would be 8. It's the number that's halfway in between. Well, you'd be getting there, sort of, but it would be incorrect because, like I said, the two samples are not of equal size, and so they should not exert equal weight on the weighted mean. The weight is the sample size. So in that case, because 7 came from a sample with more observations, the final weighted mean gets pulled farther in this direction. But once again, we have a situation where that mean that's gotten pulled down here represents a balance point between these two sample means. So if we wanted to find the balance point between the mean of sample 2 and the mean of sample 1, it would be 7.5, which is the weighted mean. So just to review, the mean tries to find a kind of balance or compromise between all of the observed values. But because of that, unlike the mode or the median, the mean does not have to be a value that we could have actually observed. So a kind of classic example of this is that while it is possible for the mean number of children in the United States to be 2.3, it is obviously impossible to have 0.3 children. You can only have whole numbers of children. So the mean may be a useful summary, but that doesn't mean that it's necessarily the best guess for a value that you might observe. And to kind of further illustrate this point, I'm going to take a look here at how distribution shape, so something we were talking about a lot last week, influences the different measures of central tendency. Because depending on the shape of the distribution, the mean, median, and mode will be in different orders and may convey different kinds of information about the underlying distribution that you're concerned with. So if we remember our histogram of finishing times here, we found that the modal interval was between 14 and 15 hours, so around here. The median is a bit less, a little over 13, and the mean was a little under 13. So, like I said, it's kind of pulled out towards these exceptionally fast finishing times and away from this big hump of somewhat slower finishing times. And this is actually generally the case for any negatively skewed distribution. So anytime you have a distribution that has this form, the mode will be somewhere, the mean is going to be pulled out toward the tail, and the median will lie in between the mean and the mode. And it's just a perfect mirror situation when you have positively skewed distributions. So here's the mode of our positively skewed distribution. The mean is pulled out toward the tail, and the median lies in between. So this is, again, kind of the behavior of the mean trying to find a compromise between all the observed values. So the mean is going to say, well, okay, sure, there's a lot of observations here at the mode, but there's this really long tail here, and it would be unfair to leave that tail out. So I'm going to incorporate some of that, some of the observations out there in the tail, and kind of find a balance or compromise where we are giving some weight to the mode, but then also weight to the tail as it goes farther out. And then the median it always tends to lie between the mode and the mean for these kinds of skewed distributions. Now, for a non-skewed, that is a symmetric distribution, we know that the mode is the most commonly observed value, right? So it's always going to be here. So yeah, again, this is a symmetric distribution. Has a nice mode here, single mode. So I will ask you guys and give you a pause to think about it. So given this, where would the other values be? Where do you think the median would be for this kind of distribution? And where do you think the mean would be for this kind of distribution? So to remind everyone, although the mode is the most common value, the median is the one that is the midpoint of the data. It splits the observations into two equal halves. And the mean, is the balance point of the data. It tries to find a compromise between all the observed values. So thinking about that, where would the median and the mode be in this kind of distribution? This also gives me an excuse to have another sip of coffee. Excuse me. Well, now I'm giving you some time. It turns out the median and the mean are all in the same place as the mode, which is to say the mode, the median, and the mean will all be the same for a symmetric single mode distribution. But this isn't necessarily the case for all symmetric distributions. So imagine that we had something like this. So if we recall from last week, this is called a bimodal distribution because there are two peaks. And in this case, those two peaks happen to be of equal height. So the median, in this case, is once again the midpoint of the data. So you can see why this would be the median, right? Because if you fold the data here, right at the seam, they'll fold right on top of each other. It's exactly the midpoint. Half of the things are below, half of the things are above. That's pretty nice. But the mean is going to end up being in the same place, at least if the two modes are of equal height. So this, for this, you can kind of think of it as being, well, as being like the weighted mean example that we had earlier. So imagine that we only saw a single mode of this distribution. So we only saw the left side of this distribution. Well, we could compute a mean from that would be fairly close to here, but because we're just cutting it off right here, that does mean that it would be a little bit skewed to the right, so our mean might be pulled out a little bit. Pulled out a little to the left here. I meant to say left in that last line. So the mean might be pulled out a little bit to the left. The mean might be pulled out a little bit to the right if we computed one that was based only on this side of the data, only on this half. But the overall mean is just a weighted mean of those two subgroups. But in this case, the two subgroups have the same sample size. So because the left and the right half are perfectly symmetrical. So if we have a situation like that, well, then that's just the midpoint between the two means, which turns out to be this kind of fold, the point at which this distribution folds on top of each other. So median and the mean end up in the same place for a symmetric bimodal distribution. This will not be generally the case for any bimodal distribution, but it will be the case for a symmetric one. The trick, though, is that we have these two modes. So it's no longer the case that the mode, the median, and the mean are right on top of each other, as they are for a single-moded symmetric distribution. So this is just to illustrate that in general, when you've got a median and a mean that lie on top of each other, well, that's a good sign that your distribution is symmetrical, but it's not necessarily a sign that it is unimodal. It's not necessarily a sign that there is only a single mode in your data. So, to summarize, for symmetric distributions, the mean and median will always be equal, but the mode is only going to be equal to the median and the mean if the distribution has a single mode. If it doesn't, then yeah, you've got a little bit more work cut out for you. But fortunately, distributions in real life, tend, at least in the situations that we're going to examine, tend to be of the unimodal variety. But it's entirely possible to obtain data from multimodal distributions like this, so it's something that you always have to be kind of keeping your eyes open for. So now let's think about all of these different measures together. So last time we compared the mode and the median, and now we've introduced the mean as a measure of central tendency. Just to remind everyone of the definitions. So the mode is the most common observed value. The median is the value that divides the set of observations in half. And the mean is the balance point of the distribution of observations. So they all have different definitions, but I think you can agree that they all are plausible candidates for a good description of the central tendency of our data. So last time we talked about how the mode can be applied to any kind of data, because there's for nominal and ordinal scales, because those are kind of qualitative scales. There's always going to be a most frequent value. There may be a tie, but there will always be at least one mode for that kind of data. And for interval or ratio scale data, you can always construct a grouped frequency distribution and find the modal interval. So the mode is sort of the thing that you can apply to any kind of data. The median is a bit more restrictive because it can only be applied to data that have an intrinsic order. So that would be, for one thing, of course, ordinal data. So if you have ranks or something like, or preference scales and things like that, then ordinal, that kind of ordinal data, the median will work for you. And of course, interval and ratio scales are quite easily done with the median. It's just a matter of going through the mechanics of putting your observations in order, counting along until you find the point at which there are an equal number of observations above and below, and that's your median. Now, the mean is more restrictive still. The mean can only be applied to interval or ratio scale data. Now, thinking about how the mean is defined may let you know why that is. So remember that to compute the mean, we have to add up the observations that we've had. So addition needs to be something that has meaning for whenever we're trying to compute the mean of something. In other words, you need to be able to have a situation where 3 plus 4 has some kind of meaning. Now that's not the case for instance, nominal variables. You can't add two names together and get a name. That doesn't make any sense. Ordinal scales, you generally can't. You can't add together, for instance, the first and second place winners of a race and get a different winner of the race. That's just not possible. So the mean can only be applied to data for which the operation of addition, putting together two numbers, makes some sense. And that is only the case for interval or ratio scale data. Now, I'm quite a stickler about this. I know that the book, as well as many practitioners in the field, will take means of ordinal scale data. In other words, means of where the data lie on a scale where you can put the observations in order from smallest to largest, but the difference between any two values is not meaningful. So the quintessential example of ordinal data of this kind is the set of winners of a race. So you can put them in order, but first is better than second is better than third, but the amount by which the first is better than the second is not necessarily the same as the amount by which the second is better than the third. But people nonetheless will try and compute means on that scale. This is mostly just a warning to say that it'll probably come up at some point, either in one of the book examples or in something you happen to encounter when reading some research or something like that. But like I said, I'm quite a stickler, so I only advise that the mean is applicable to interval or ratio scale data. So thank you for allowing me to rant there for a little bit. I will move on. So, as we saw last time, the mode and the median, but by virtue of having a kind of myopic view of the data, of either only looking at the most common value or only looking at the midpoint, the mode and the median are not very sensitive to even drastic changes in the underlying data. So if you have wildly skewed data, or if you have lots of outliers that seem kind of unusual, the mode and the median are not generally going to care about those sorts of observations that much. The mean, on the other hand, is extremely sensitive to changes in data because, as I've been trying to emphasize all day, the mean uses every single observation when you're computing it. You have to add together every single observation that you've got, and that's the precise value of the median or the mode doesn't depend on every single observation, only on the ones that are either the most common or the ones that define the midpoint of the data. So now we can, given these different properties of these different measures of central tendency, we can think about situations where we would tend to use these in particular. So like I said, there are some hard rules. For instance, you can't compute means on nominal or ordinal scales, but there are some times where things may be a little bit more ambiguous, and so you just kind of have to go with a rule of thumb about which is the better measure of central tendency to report in each case. Of course, the best thing to do And what is often done is just to report all of them for any particular set of data to let a reader kind of decide for themselves what they think is best in any one case. But to begin, talking about the kind of hard rules, well, the mode, if you've got nominal scale data, like for instance, if we remember these, this is the states of origin for all the 60 finishers of the 2015 Virtual Crest 50-mile course. And this is a nominal scale data, or nominal scale variable. The only thing you can do with this is find the mode, which in this case is New York. Can't find a median because there's no order that you can impose on this, at least no meaningful order. You can't find a mean because you can't add two states together and get another state. So you can't add together New York and Pennsylvania and get another state. You don't get Texas from that, for instance. That just doesn't make any sense. So you can't do a mean, you can't do a median, but you can do a mode when you have nominal scale data. Now, I mentioned that the mode can indeed be applied to any measurement scale, but for interval or ratio scales, you need to use grouped frequency distributions in order to find a modal interval. But as we've seen, although there are rules of thumb for defining the width of the class interval that you use to construct these grouped frequency distributions, they are just rules of thumb, and they are, to some degree, subjective. And usually they, of course, also depend on the kind of data you have. So you're going to make, as we saw in the example of how you get smooth frequency distributions when you have lots of data. If you have lots of data, you can make the bins, or excuse me, the class interval bins, you make them really, really small, which is going to give you a different modal interval than if you made the bins really, really big, maybe because you had relatively few data. So because of that subjectivity, the mode is not usually used as a measure of central tendency for interval or ratio scale data, though again it's still entirely possible to do. Instead, we might think of, well, okay, maybe let's have the median. So the median is something that, of course, can be applied to interval ratio scale data as well as ordinal data. And indeed, for ordinal data, it is because, as I've tried to emphasize, because you really shouldn't compute means for ordinal scale data. If you happen to have ordinal data, the median is usually going to be your best summary for that kind of data. But even when it's not ordinal, when it is interval, or in this case ratio scale for the finishing time data, the median can be useful when you have skewed distributions. So this last time we were debating about whether this was bimodal or just negatively skewed. Like I said, it's kind of a judgment call on that one, but either way, it's clear that there's lots of observations that are not necessarily all that close to the mode. So when you have a skewed distribution, the median can be useful for kind of finding a point at which that distribution can be cut in half in a meaningful way. So we've got this kind of tail here of exceptionally fast runners, and this hump here of kind of more normal, people like me, slower runners. And the median is a good balance, it's a good way of splitting up those two kind of groups, the hump and the tail of the distribution. So for that reason, it can be useful for skewed distributions, even if they're not strictly bimodal. It's also useful in situations where you know that you have outliers who are not necessarily representative of the group. So we have this one exceptionally slow runner here who surprisingly was not me, but so it goes. And we have this exceptionally slow runner. Does it seem like they are really representative of the whole group of runners? Well, in this case, yeah, probably. I mean, maybe if we had more people running the race, we would have observed some more people in this gap here in the 16 to 17 hour range. That would kind of make this seem a bit less exceptional. But there's there are circumstances, for instance, if this person really had taken 24 hours to finish, that would be exceptionally long. And we really wouldn't want our measure of central tendency to be overly influenced by that kind of outlying observation. So in that case, the median is your friend, because the median only cares about the midpoint of the distribution. It doesn't really care if you've got outliers that are way out here or way out here. So when you have outliers like that, the median is often the measure of central tendency to use. Now, the problem, though, is that the median can be misleading because it isn't influenced by all observations. So, on the one hand, maybe you don't want your measure of central tendency to be influenced by outliers, but on the other hand, you don't always know what counts as an outlier. So, is this one person 17 to 18 hours, that really an outlier? Or would it not matter if they had really taken a really long time? Or should we take that into account? Should we say, okay, yeah, this is a reasonable time that should enter into our consideration of the central tendency of this distribution? So, to give a different example, this comes not from the Virgil Crest race, but from a different project that I worked on. It's as part of a larger project, but we had, in this case, a personality questionnaire that was given as part of the experiment, and we can construct a histogram of these scores. In this case, a class interval width of 6 is actually meaningful for this particular kind of scale, so I picked that. I know it's maybe not a round number, but it makes sense for this kind of data. And the mean, which lies about here, a little bit over 18 of this personality inventory, is a good summary of this kind of data, rather than, say, the median or the mode, because the mean is good for kind of unimodal and symmetric distributions. And in particular, it's good for situations where you have no reason to discount any observations as being outliers. So here, when we're looking at the finishing time data, we might have reason to believe that this exceptionally slow person really shouldn't inform our guess about the central tendency of the distribution. But when we have data that looks like this, there's no obvious outliers, and it's a fairly it's a fairly large data set, and it's also computed on using a personality test that has been kind of tweaked and prodded for a long time. So the data from this kind of thing, there's no reason to discount any one observation. So sure, you might have some people that are exceptionally low or exceptionally high, but they don't look like they're outside of the realm of possibility. So when you have no reason to discount any observation, you should usually report a mean, as long as, again, you're on an interval or ratio scale, because that incorporates information from every single observation that you've obtained. Now, the downside to the mean is that it can yield values that could never be seen in real life, as we've seen in our couple of examples so far. So, why is that a problem? Well, it can be a problem if, for instance, you're trying to guess what are what are typical scores. Well, if you've 2.3 children is not actually typical of anyone, because it's impossible to have 0.3 children. So that calls into question whether the mean is really a good summary for how many children American families tend to have. Perhaps a median, which is an observed value, would be more informative. So if the median number of children is 2, that might be actually more useful summary of the data, because 2 is a number of children that is possible to have, whereas 2.3 is not. So, like I said, these considerations are things that you always kind of need to have in your mind when you are thinking about what kind of measure of central tendency to report based on a particular data set, and it really is up to your judgment, your informed judgment, which is the better measure, aside from these rules about measurement scales that I've talked about up here. But the way that you get that informed judgment is to do this, and do this a lot of times. So this is where, again, the homeworks come in. This is where doing the practice problems in the book come in, because you really just got to do it and build up those, build up that intuition in order to see where these different measures of central tendency are best applied. So, to go back to our kind of set of questions about what statistics is about that we talked about even on the very first day. The measures of central tendency, whether the mode, the median, or the mean, can give you a best guess about what values are typical or representative of your data. And like I was just saying, how good of a guess that is depends on the kind of data you have, as well as which of these measures you use. But the other thing that we need to know from statistics is not just what's your best guess of what you could observe, but you also need to know how far off that best guess could be. So to give an example, imagine we had data that looked like either this or this. So here I've just constructed a simple histogram. This is fake data, but in either case, the mean is pretty close to 0 in each case. But it seems like in the left case, if you guessed, okay, my best guess for what value we would observe is 0. Well, it seems like that's a better guess in the left situation than it is in the right situation. So in the left situation, data tend to fall between -3 and 3, so that's not too far off from 0, which is our best guess based on the mean. But in this case, oh man, it's all over the place. It goes -11 all the way up to 11. It's kind of spiky. Mean is still 0, but is that an equally good guess in this situation relative to this situation on the left? Well, I think you will agree that no. In this case, we're liable to be much farther off with our best guess in the right scenario than we are in the left. So, a good summary of the data should tell us not only what values are typical or representative of the data, but also how much the data tend to vary around those typical values. And that's going to be our topic for next week. How do we measure and report the degree to which observations vary around their central tendency? So in the not too distant future, remember that we've got lab going on tomorrow, and as usual, there's a homework assignment due on Applia on Sunday night. This is about measures of central tendency, that sort of thing. And you'll need to read Chapter 4 on the topic of variability in preparation for next week's section. So thank you very much, everyone. Thank you again for dealing with virtual Greg. I do appreciate your patience in this. I wish I lived somewhere where it was possible to just drive out whenever I could, but sadly we live in upstate New York. So thanks again, everyone, and I hope to see you in person next week.